Hello and welcome to our atmospheric waves experiment, which we call AWE. My name is Mike Taylor and I am the proud PI of this exciting program. AWE is a new NASA mission of opportunity designed to investigate the global properties of short-period gravity waves and quantify their impacts on the upper atmosphere. In a nutshell, AWE will fly a state-of-the-art infrared imager on the International Space Station to gain a transformative set of gravity wave measurements at the gateway to the ionosphere-thermosphere system. This slide shows a cross-section of the Earth atmosphere and overlying ionosphere. The black squiggles represent gravity waves generated by severe weather, such as jet streams, thunderstorms, wind forcing over large mountains, and hurricanes. As these waves propagate upwards, they grow in amplitude due to density decreases, and eventually break, depositing large amounts of energy and momentum. This occurs primarily at the Mesopause region, indicated by the reddish Airglow layer near 90 kilometers. This is where AWE will focus its measurements. Some waves also propagate to higher altitudes, directly into the ionosphere. Together, they show how terrestrial weather translates into space weather, strongly affecting GPS navigation, tracking, and communications of high societal importance. We now know that it's the small-scale gravity waves with horizontal wavelengths 30 to 300 kilometers, which can rapidly transport large amounts of momentum into the ITM that contribute to its variability. AWE has three primary objectives to investigate these waves. The first is to quantify the seasonal and regional variabilities and influence of gravity waves near the Mesopause region. This we will do using global gravity wave measurements of the fluxes. The second will identify the dominant dynamical processes controlling the gravity waves, and we'll study this by identifying the dominant sources and their propagation into that region. And the third is to estimate the widespread role of gravity waves in the ITM. We will do this by direct penetration of waves directly into the ionosphere. In summary, global small-scale gravity wave measurements are essential but severely lacking. This slide shows a beautiful image of the Earth looking down over the southwestern USA from the ISS. Note the green glowing layer visible in the limb that completely surrounds the Earth. This is a naturally occurring airglow emission layer. There are several different color airglow layers surrounding the Earth. For our AWE mission, we will image the OH infrared layer at approximately the altitude of 87 kilometers, which is the brightest emission but is not visible to the naked eye or to photographic cameras. I like to think of this layer as nature's gift to us, as it is an excellent tracer for gravity waves as they propagate into the upper mesospheric gateway region. This slide shows an image of a beautiful example of a gravity wave event imaged in the OH layer as seen looking down from a high altitude satellite passing over Texas. In this example, the gravity waves appear as circular rings emanating from a cluster of storms, like pebbles dropped in a pond. Our AWE mission will not only measure structure and brightness of the waves, but also their temperature amplitudes for estimating their fluxes using well-established ratio technique. This slide shows how we measure temperature amplitudes of the gravity waves. The image on the left shows our AMTM, Advanced Mesospheric Temperature Mapper, developed at the Space Dynamics Laboratory at Utah State University for ground-based measurements. The AMTM is a highly successful instrument and has operated at the South Pole for the past 10 years automatically. A well-established ratio technique is used to determine temperature amplitudes. This is shown in the central plot, which shows part of the OH31 spectrum from 1500 to 1560 nanometers. By taking the ratio of two emission lines, e.g. P12 and the P14 as indicated in red, the absolute rotational temperature can be directly measured from a relative brightness ratio that has been background corrected. In operation, the AMTM sequentially measures the P12, P14 and background using a filter wheel and typically a 10-second exposures. As these emissions are in local thermodynamic equilibrium, the rotational temperature yields a good estimate of the atmospheric temperature at the OH layer height. The figure on the right shows an example temperature map. Note the 40-degree temperature range and the high quality of the data. This map in intensity and temperature will be an OR level 2 data product. Gravity wave energy and momentum fluxes are derived from these temperature maps. Most observations of gravity waves to date continue to be obtained over land. This slide demonstrates the importance of extensive airborne observations over oceans and inaccessible lands, such as mountains. This movie shows the development of a data swath as an NSF aircraft underflies the OH layer. The data were obtained during the highly successful DEEPWAVE mission in 2014, flying over New Zealand, showing both large and small scale waves extending over lands and oceans. It is important to note that OR will have a swath width of some 600 kilometers greater than the flight track shown here, and 10,000 kilometers long. OR will have an exceptional global coverage with 15 swaths per day, constituting a level 3 data product. This slide shows the solid drawing of the AMTM currently under development at SDL for flight on the ISS. The instrument uses the same principles as our ground-based AMTM, but multiple telescopes are used to obtain images of the OH emission lines at the same time, using a 1-second exposure to investigate 30 to 300 kilometer gravity waves. The field of view of the OR instrument will be 90 degrees, that's equivalent to 600 kilometer footprint. It's 1 meter long, and an engineering model is currently under development. This graphic representation shows the planned location of OR on the ISS, indicated by the dashed red circle on the far right of the platform. The AMTM will observe the NADAR from ELC-1 platform Site 8 with a 90-degree field of view. 2 years of observations are planned from mid-2022 to mid-2024. The figure on the left side shows examples of gravity wave sources that will be observed by OR, essentially all types and in both hemispheres. Observations up to plus or minus 55 degrees latitude will enable exceptional coverage, including the well-known hotspots over the southern Andes to be measured. The right-hand figure shows full nighttime coverage every 4 days and full local time coverage every 30 days. A 2-year baseline mission will enable seasonal, interannual and interhemispheric variability studies. Our OR measurements will be highly complemented by 4 state-of-the-art models, 2 global and 2 regional. Our OR co-investigators are experts in these models, which will be used together with OR data to derive global gravity wave energy and momentum fluxes. That's our objective 1. Apply all 4 models to understand linkages between sources and observed gravity waves, our objective 2. And then to quantify their impacts on the ITM region using well-defined deep penetrating wave events. Together, this will create a transformative investigation of gravity waves and their impacts on a global scale. In summary, OR is a 2-year mission scheduled to be launched in July 2022. Our measurements are nighttime with full coverage over the latitude range of the ISS every 4 days. The ISS is an ideal platform for us in terms of mass, power, orbital coverage and data requirements. A 600 kilometer field of view enables comprehensive gravity wave measurements from our atmospheric maps. In addition, state-of-the-art modeling using 2 global and 2 regional models already exists. Our co-investigators are all experts in these measurements. We are planning coordinated ground-based observations in Utah, but also want to offer you to join us from wherever you are around the world, looking upwards as we fly over you. All data will be archived in the NASA SPDF facility available to everyone. This will be the first NASA Heliophysics instrument on the ISS, and we are really looking forward to this exciting mission. Before closing, I would like to introduce our student collaboration program, which will be conducted in parallel with our OR mission. This collaboration includes students from Utah State University and Embry-Riddle Aeronautical University. Working remotely together in teams, they will investigate the occurrence and properties of gravity waves observed at the mesopause and their occurrence and signatures in the overlaying ionosphere. This is illustrated in the diagram, which shows a simulation of a gravity wave spectrum extending through the ITM from the OH layer to over 300 kilometers in the ionosphere, where it is detected as a medium-scale traveling ionospheric disturbance, or AMTM. At USU Bear Lake Observatory, students will operate an all-sky OH imager measuring gravity wave events in the mesopause. A second camera will detect these waves in the thermospheric red line emission at 250 kilometers altitude if they are present. At Embry-Riddle, students will use ground-based GPS TEC to investigate ionospheric signatures of the potential TID over Utah and to the greater USA. Using our models, the students will study the connectivity between these two regions. I would like to conclude with this NASA slide, which shows their impressive Heliophysics system observatory. Over the past nearly 2 decades, I have had the opportunity to work with the TIME satellite as a ground-based observer, and more recently with the AIM satellite as a co-investigator studying gravity waves in polar mesospheric clouds. So it's really exciting to see OR shown here on the ISS under formulation. In 2022, OR will become the first heliophysics mission on the ISS. Finally, my OR colleagues and I would like to thank CEDAR for arranging this virtual workshop. It's for sure that we are all currently experiencing a new way of work and life. I look forward to the new times when we can all meet together again at CEDAR and other conferences to discuss exciting new collaborative results of our OR mission. Thank you and see you next year.